Hello and welcome to Controllers Tech. In the previous video, we saw how to create multiple tasks with different priorities. Now that we have multiple tasks running in the system, the next step is to allow these tasks to communicate with each other. For example, we might want to send some data from one task to another. A common mistake when implementing this is using a global variable to share data between tasks. For example, say I have a structure that will be updated by two different tasks, and it will be consumed by a third task. Now let's say task 1 updates the data in the structure, and we expect the consumer task to read this data. At the same time, task 2 can also update the data in the same structure, and the consumer task will read that data as well. The problem here is that a race condition can occur. In this situation, the data can get corrupted. The consumer task may end up reading the data written by task 2, even though it was actually expecting the data from task 1. To solve this issue, we should use a more reliable method of communication between tasks. FreeRTOS provides queues specifically for this purpose. Think of a queue as a small buffer that can store multiple messages sent by different tasks. In this example, we will configure the queue to hold 10 elements. So you can imagine it as 10 slots, where each slot can store one message. Now suppose task 1 generates some data and sends it to the queue. The data will be placed in the first empty slot of the queue. Next, if task 2 generates data and sends it to the queue, it will be placed in the next slot. Both tasks can continue sending data, and the queue will keep filling up one element at a time, until all 10 slots are filled. If the queue becomes full, then any new message sent by task 1 or task 2 will have to wait until some space becomes available in the queue. Now on the other side, we will have a receiving task. Its job is to read the messages from the queue. Whenever the receiving task reads one message, that message is removed from the queue, which means one slot becomes free again. Another important thing about queues is that they follow the FIFO rule, which stands for first in, first out. This means the first message that enters the queue will also be the first one to leave it. So if task 1 sends a message first and task 2 sends another message after that, the receiving task will first read the message from task 1, and then the message from task 2. Now let's say we have a queue. Task 1 writes the data into the structure and then pushes that structure into the queue. The consumer task will read the structure from the queue. If task 2 wakes up and writes new data into the structure, it will also push its structure into the queue. This data will simply be added to the queue as another element. So the consumer task will first read the structure sent by task 1, and then it will read the structure sent by task 2, in the same order they were placed in the queue. In this video, we will see how to create a queue, how to send data to the queue, and how to receive data from it. We will also look at what happens when the queue becomes full, and how to handle different situations when the queue is full or empty. Let's start with the project we created in part 2. Here you can see that the project has already been loaded into the IDE, and it is the same project we used in the previous video. The first thing we will do is rename it to part 3. While renaming, make sure to check Update References, so that all the relevant names are updated automatically in the project. Alright, the renaming is done. Now we will delete the debug configuration and also rename the IOC file so that it matches the project name. Before we proceed further, let me quickly give a brief overview of the example we are going to implement in this video. We will create two different tasks, and both of them will write data into a common structure. After updating the data, each task will push that structure into a queue. There will also be a receiving task, which will read the data from the queue and print it through UART. For printing, we will use the printf function. This will make debugging easier, and it will also be useful for debugging in the upcoming videos. Now let's take a quick look at the schematic of the L496 board. Since this is a Nucleo board, we can use the virtual COM port to route the UART data through the ST-Link USB connection. Here you can see that ST-Link RX is connected to low-power UART1TX, and ST-Link TX is connected to UART1RX. These correspond to pins PG7 and PG8, so we will keep this in mind while configuring the UART in CubeMX. I am also going to use a button to update the data in the structure. The button will be connected between pin PA3 and ground. The pin will be pulled high by default, and when the button is pressed, it will be pulled low to ground, indicating that the button has been pressed. Now let's open CubeMX to configure the project. Load part 3 into CubeMX. First, disable all the LED pins that we configured in the previous project, since we will not be using them anymore. Next, configure pin PA3 as GPIO input, since this is where the button will be connected. Now go to the GPIO configuration, and set the pin to pull-up mode. This ensures that the pin remains high by default, and when the button is pressed, it will be pulled low to ground. Now go to connectivity and enable low-power UART1 in asynchronous mode. We will use this UART to route the printf output to the computer. By default, the pins PC0 and PC1 are assigned for this UART. However, as we saw in the schematic, we need to configure PG7 and PG8 instead. So set PG7 as UART1TX and PG8 as UART1RX. I am going to keep the baud rate at 115200. The word length will be 8 bits, with no parity and one stop bit, which is the standard UART configuration. Now go to middleware FreeRTOS and open tasks and queues. There are 4 tasks from the previous project, but we don't need 4 anymore. We will work with 3 tasks, so delete the 4th task. Let's modify task 1 first. Task 1 will send data to the queue, so I will keep its priority normal. The stack size will be 128 words, since there is not much happening inside this task. It will simply load data into a structure and send that structure to the queue. Similarly, task 2 will also have the same normal priority, and the same stack size. It will also push data into the queue. Now task 3 will be the receiving task, which will read data from the queue and print it via UART. Since this task receives the data and performs the printing operation, I want its priority to be higher than normal. We do not want task 1 and task 2 to preempt this task while it is performing the printing, otherwise the output on UART could get corrupted. Normally we would protect shared resources like UART using semaphores or mutexes, but since we have not covered them yet, I will simply set this task's priority to high. This ensures that task 1 and task 2 will not preempt the receiving task while it is printing. Since we are using printf, we also need a larger stack size. Set it to at least 512 words, which is about 2 kilobytes. The printf function requires more stack space, so you should adjust it accordingly. You may try lower values, but make sure to test it properly. After doing this, you will notice an error in the heap usage, showing that the available heap has been fully utilized. So go back to parameter configuration and increase the heap size. I will set it to around 5 kilobytes, and now the error disappears. We now have enough heap available. Inside the same tab, we also have the option to add a queue, so let's add one. I will name it message queue. The queue size defines how many elements the queue can store. We do not need a very large size, but since 2 different tasks will be sending data to the queue, let's keep it at 10. This means both tasks can send up to 10 elements in total, after which the queue will become full. Once the receiving task reads data from the queue, space will become available again. The item size represents the size of the data being stored in the queue. You can use data types like integers, characters, 32-bit integers, or any other type depending on what kind of data you want to send. In this example, I will use a structure that contains two elements: an 8-bit unsigned integer, and a 32-bit unsigned integer. Since we cannot define a structure type directly in CubeMX for the Q item, we will manually modify it later in the code. The allocation will be dynamic, so the memory will automatically be taken from the heap. If you check the heap usage, you can see that the message Q is consuming 132 bytes. Out of these 132 bytes, about 40 bytes are used by the Q items, and the rest is used for the internal queue management. Since we still have sufficient heap available, this configuration is good to go. That is all we need to configure here. Now click Generate Code to generate the project. Now let's go back to the IDE. Inside the main function, you can see that a message queue has been created along with 3 different tasks. Also note that the data size of each queue element is currently set to 32-bit integer, just like we configured in CubeMX. As I mentioned earlier, I am going to create a structure that will contain 2 data types: an event ID of 8-bit unsigned integer type, and a timestamp of 32-bit unsigned integer type. Task 1 and Task 2 will write their data into this structure. Now, since we want to transmit this structure to the queue, we cannot keep the queue element type as a 32-bit unsigned integer. This is the difference between a simple queue and a structure queue. If you only want to send a single 32-bit value, you can keep the queue type as 32-bit unsigned integer. But since we want to send a structure, we need to change the queue element type to our message structure. The queue will still contain 10 elements, but now each element will be one structure. So in total, the queue can store 10 structures at a time. As I mentioned earlier, we will use printf to print the data to the serial console. For this, we need a custom function that routes the printf output through UART. Inside this function, we will call HAL UART transmit to send the data through UART, one character at a time. So whenever printf prints something, it will internally call this function, and that function will transmit the data through UART. Now let's write the task functions. First, we define a local message structure that will store the data which needs to be sent to the queue. Inside the infinite loop, we check if the button is pressed. Since the pin is pulled high by default and goes low when the button is pressed, we will check if pin PA3 is low. If the button is pressed, we store the data inside the message structure. The event ID is set to 1, indicating that this event is generated by task 1. The timestamp is obtained using the function HAL-getTick. After storing the data inside the structure, we call OS message queue put. This function is used to put a message into the queue. The parameters are queue handle, to which we want to send the message. Message pointer is the address of the structure we just created. And message priority defines how urgent the message is. In CMSIS-OS queues, messages can be assigned different priorities. Messages with higher priority are placed ahead of lower priority messages in the queue. So if multiple messages are waiting in the queue, the ones with higher priority will be read first. In our example, we will simply keep the priority 0, since this is not a priority-based message. The last parameter is the timeout. This defines how long the function should wait if the queue is full. For example, if the timeout is set to 1 second and the queue is already full, the function will wait for up to 1 second for some space to become available in the queue. If the queue does not become empty within this time, the function will exit and return a failure code. If we set the timeout to OS wait forever, the function will wait indefinitely until space becomes available in the queue. This can be useful in situations where the message must be sent, no matter how long it takes. On the other hand, if the timeout is set to 0, the function will not wait at all. It will check the queue. If there is space, the message will be added, otherwise, the function will return immediately with a failure code. After sending the data to the queue, we add a small delay. This helps with button debouncing, and also ensures that the task does not run continuously without yielding the CPU. Task 2 will have a similar logic. It will also push data into the queue. Here, we will first define a local message structure. However, instead of checking the button, this task will simply load data into the queue every 1 second. I am using a different event ID to indicate that the data is coming from task 2. I am also converting the timestamp to seconds, just to clearly differentiate it from the data generated by task 1. After storing the data inside the structure, we again call OS message queuePut, to place this structure into the queue. This loop will run every 1 second. So basically, if the button is not pressed, task 2 will still send data to the queue every second. If the button is pressed, then task 1 will also start sending data to the queue. Now let's look at the receive task. The job of the receive task is to read data from the queue and print it on the serial console. So here as well, we first define a local message structure. Next, we call the function OSMessageQueueGet. This function reads data from the queue and stores it in the message structure that we just defined. The parameters are similar to the previous function, but their behavior is slightly different. The timeout parameter works as follows. If we set the timeout to 0, the function will immediately check the queue. If data is available, it will read the data, otherwise, it will return an error code. If we use OSWaitForever, the function will wait indefinitely for data to arrive in the queue. If the queue is empty, the task will be blocked until some data is written to the queue. As soon as data arrives, the function will read the data, store it in the message structure, and return the success code, which is OSOK. So if the data read is successful, we will print the data to the serial console. Here, I am printing both the event ID and the timestamp. That is all we need to do. Now let's build the project. We have an error related to the definition of printf. To fix this, we need to include the standard IO header file in the main file. After including it, all the errors are gone, and the project builds successfully. Now we are ready to test the project. Let's flash the code to the board. Now open the serial console to view the output. Make sure that the console configuration matches the UART settings we configured earlier in CubeMX. Here you can see event ID 2 being printed continuously every second on the console. This data is coming from task 2, which is periodically sending messages to the queue. You can also notice that the timestamp is in seconds, which is how we configured it in task 2. Now when I press the button, the data from task 1 is also printed immediately. You can identify it by event ID 1, and the timestamp is in milliseconds. So at this point, both tasks are sending data, and the receive task is reading that data from the queue and printing it on the console. This shows that the queue is working correctly and the communication between tasks is happening properly. Let's also take a quick look at some other queue-related functions available in CMSIS-OS version 2. We have already seen two important functions. OS message queuePut is used to put data into the queue. OS message queueGet is used to retrieve data from the queue. Now let's look at a few additional functions. OS message queueGet capacity. This function returns the total number of elements that the queue can hold. For example, in our case we configured the queue to store 10 elements, so this function will return 10. OS message queueGet message size returns the size of each message stored in the queue. OS message queueGet count returns the number of messages currently waiting inside the queue. For example, if task 1 and task 2 both push one message each, and the receive task has not read them yet, then the queue will contain 2 messages, and this function will return 2. So it simply tells us how many messages are currently waiting in the queue. OS message queue_get_space returns the number of free spaces available in the queue. Continuing the previous example, if 2 messages are waiting in the queue, there are 8 empty spaces available, and this function will hence return 8. Now let's see how these functions can be used in practice. Before reading a message from the queue, we can call OS message queue_get_count. This function tells us how many messages are currently waiting in the queue. If the value is greater than 0, then we proceed with OS message queue_get to read the data. Otherwise, we simply skip the read operation. This approach allows us to avoid using a blocking call while reading data from the queue. Similarly, before pushing data into the queue, we can check if the queue has free space available by calling OS message queue_get_space. This function returns the number of available spaces in the queue. If the value is greater than 0, we can safely push the message into the queue. Otherwise, we can handle the situation differently, depending on the application. There is one final function, OS message queue_reset. This function resets the entire queue. It removes all the messages currently stored in the queue, effectively emptying it completely. So this is how inter-task communication works using queues. Queues provide a much safer and more structured way of transmitting data between tasks compared to global variables. As mentioned earlier, using global variables can easily lead to race conditions, especially as the project becomes more complex. Using queues helps avoid these problems and provides a more reliable communication mechanism between tasks. I hope you understood how queues work and how they can be used for communication between tasks. You can download the project from the article linked in the description of the video. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.